students, so this lesson is 2.3.2 and we're going to be focusing on 7-segment displays. So the big concept of this lesson is that you're going to learn about the function of 7-segment displays and the driver IC chip that we use to control them within a circuit. So this is actually going to be broken into 2 parts. The first is going to focus on just the 7-segment display, and then part 2 is the driver. We're going to need both for our lesson tomorrow, so let's get started. So first, again, we're looking at just 7-segment displays, and a 7-segment display is a display that can be used to display a decimal number 0 through 9 and some alpha characters. We have 2 different types. There's a common anode and a common cathode. And then we also need a resistor tied to each input of this 7-segment display because they're essentially tiny LEDs bonded together through the chip work inside. So looking at how we control a 7-segment display, so it's actually a figure 8 grouping of LEDs, and sometimes it also includes a decimal point. But each segment is labeled A through D. So you can see the way it's labeled down here. So at the top it goes, so it just basically goes around in a clockwise pattern. So it's A, B, C, D for the bottom and the decimal point, E, F, and G is the center. So all of the segments or individual LED are labeled by a letter. So again, we have common cathode, which means all the LED cathodes are connected, or common anode, which means all of the anodes are connected. So what that means is just how are these put together? So you can see this is the pin out for the common cathode. So we basically have so basically we've got A, and then B, C, D, and then E, F, and G in the center. And again, you can see we've got ground down here, and then here we have VCC and VCC where we have these 2 grounds. So these are the digits that we can display for our 7-segment display. So like I said, it can do 0 through 9 without a problem. And then we also have select alpha characters. So we can have a lowercase b, a capital C, a lowercase d, a capital E, a capital F, capital H, capital I, capital J, capital L, lowercase n, lowercase o, capital letter P, lowercase r, a S, which does look just like a 5, capital S, I might add, a capital U, the capital Y, and then a capital Z, which does look just like the 2. So really quickly, let's just talk about basic LED operations, because essentially a 7-segment display is just LEDs grouped together. So to understand how a 7-segment display works, we have to review how that LED works. So basically, to get an LED to turn on, the anode has to be at a higher voltage potential, about a 1.5 volts, than the cathode. And the amount of current flowing through the LED will determine the brightness of that LED, or its luminosity. And the amount of current is controlled by a series resistor. So down here you can see we have the cathode, the anode, these lights symbolize its luminosity, and our current flow. So we're going from anode to cathode. The resistor is not shown in this graphic. So this is the LED configuration with the anode at 5 volts. So basically we have the switch at 5 volts, okay, so we would use digital constant, etc., or just have a 5 volt power setup with our switch. And then we would have the 220 ohm resistor going into our LED, and then 5 volts on the other end. So when we have when the switch is at, so when we have the switch at 5 volts, which is the top circuit, the LED is off. You can see it's not firing. When we have the switch at 0, such as as you see on the bottom circuit, the LED is on. So the anode being at 5 volts lights the resistor. Cathode is at 0 volts or nearly there. The 220 ohm resistor controls the current. So a larger resistor means less current equals a dimmer LED. A smaller resistor is more current and has a brighter LED. So let's work through an example. Looking at this 7-segment display, based upon what we have, what value would be displayed in the common anode 7-segment display? So we need to look over here, okay, and we need to look at what is connected to the 5 volts and what is connected to the ground. And then you're gonna have to go back, and if you did not jot down the little chart for the 7-segment display to see what is in each place, you're going to want to do that, because right now I can see that I have some of these connected to my 5 volts, while some of them are connected to ground, and depending on what letter they are is going to depend on what portions of the 7-segment display are visually lit. So I'm going to give you some time, go ahead and work through this, and we will go over the answer together. Okay, so now that you've had some time, let's take a look at the solution to this. So the solution is 4. If we look at the common anode, so our digits that are receiving 0 volts, meaning they're coming from the ground, that's B, C, F, and G, okay? So the segment is on because it's a common anode. So again, it's B, C, F, G, okay? Our 5-volt segments are the segments that are off because it's common anode. So that's A, D, and E. So A, D, and E are turned off. Therefore, we illuminate with the number 4. Okay, so now let's look at the cathode at the ground. So when we look at the top circuit, the LED is on. The anode is pretty much at 5 volts, and our cathode is at 0 volts. So the 220 ohm resistor controls the current. So again, we're controlling the current with this resistor. And then the larger the resistor, the less current, the less luminosity or dimmer LED. And a smaller resistor is more current, and again, a brighter LED. So looking at the bottom circuit, the LED is off, and that's because we are switched to the 0 volts. So let's do another practice problem. So this is a common cathode 7-segment display, which is what SSD stands for, by the way. So what value would be displayed in the common cathode 7-segment display shown? Again, we are looking to see what is connected to our 5 volts, what is connected to our ground, and what would be displayed. I'm going to give you a few moments to take a look at that, and then we'll go over the answer. So we are looking at the number 2 or capital letter Z, depending on what you were trying to display. So again, because this is common cathode, our segments that are on at 5 volts are the A, B, D, E, and G segments. And then at 0 volts, we have the C and F segments. So if we look over here at our map out, we can see A, B, C. C is connected to our ground. And then the other segment that's connected to ground is our F, and those are the 2 that are turned off currently. So now let's take a look at resistor values for the 7-segment display. The resistor values determine the amount of current that's flowing through the LED into the 7-segment display. This is why they're sometimes called current limiting resistors, when they are intentionally limiting current going into specifically an LED. So the amount of current determines how luminous or bright the LED will be. And if the resistor is too large, the current will be too small and the LED won't be visible. It may be working, but it's not visible because the luminosity isn't there. So if the resistor is too small, the current's also too large and the LED will be damaged. In a real circuit, which you guys aren't going to be working with, unfortunately, these get hot and they get really, really hot really, really quickly. And then they go and they don't work. So popping LEDs is a common thing when we're wiring circuits if you don't have your resistor at the right value. So how do you select that value? You have to read the data sheet for the 7-segment display that you are using, so that way you don't blow your 7-segment display. So basically, when we look at the data sheet, we have to look at the data sheet to find that resistor value. So the diagram below is a single segment of a common anode 7-segment display. So if we are just looking at one little lead for one little band out of there, whether it's the letter A, B, whatever, it's just one of those. The voltage across the LED when on is only 1.5 volts. So using Kirchhoff's voltage law, we know that the voltage across the resistor is 3.5 volts, okay? Thus, using Ohm's law, we can calculate the value of the resistor if we know that the current is flowing, or of the current that is to flow through the LED. So let's take a look at actually selecting a resistor value. So the LTS 4801JR common anode 7-segment display luminous intensity versus forward current graph is located right here, as if that couldn't have a longer name. But basically what this graph is telling us is we have forward current and relative luminosity. Okay, so if we pick a luminosity intensity of 1.5, so that's about in the middle. 2 would be the exact middle, but we'll work with 1.5. From the graph, we need current of 15 milliamps. So if we look at 1.5 right here, we know that we need 15 milliamps, okay, in order to get that luminosity. And then we can use Ohm's law to calculate the resistor that we need. So we need 233.33 ohms. The closest standard value resistor we have to that is 220 ohms. So we have to find the best match that allows that luminosity. If we went higher than the required resistance value, it would lower that luminosity. So if we're looking for 1.5 in luminosity, we need to actually go lower. So it'll be a little bit higher than 1.5, but it's still within a safe range where the LED will be able to operate. So go ahead and take a look at this. So we need to calculate the resistor value required to have a luminous intensity of 2.5. So you're going to use this graph from 2.5 to determine what current you need. Hint, hint, hint. Well, hang on, wrong row. Hint, 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 hint if we're going to 2.5. And then you need to use Ohm's law to calculate that. I'll give you guys a second to calculate it, and then we'll go over the answer. Alright, so from the graph we need 25 milliamps. Then using Ohm's law, obviously we've got 3.5 over our current equals 3.5 over 25 milliamps is equal to 140 ohms. The closest resistor that we have is 150. So obviously we're going to have a little less than our desired 2.5 luminosity because our resistor is slightly larger, but it will be minimal in terms of difference. So it'll be a negligible difference that we can just use that resistor. Again, we always have to choose the closest standard value to what we've calculated.